Today we are going to discuss the special cases of damped harmonic motion. So we know the differential equation of damped harmonic motion is d square x by dt square plus 2k into dx by dt plus omega 0 square x equal to 0. And we find out the general solution of that differential equation. We get the general solution as x equal to a1 e raised to minus k plus root of k square minus omega 0 square into t plus a2 e raised to minus k minus root of k square minus omega 0 square into t. So based on the values of this k and omega 0, what is k? K is the damping frequency and omega 0 is the natural frequency. Damping frequency and omega 0 is the natural frequency. So based on the values of this k and omega 0, we can write three cases. So the first case 1 is damping frequency is greater than the natural frequency. If damping frequency is greater than the natural frequency, consider the spring mass system. This is the spring mass system. So now it is in a frictional plane. Mass is suspended and it elongates or extend to a distance x. So this is the extreme position, x equal to a. When this damping frequency is very high, this body very slowly comes back to this equilibrium position. This is the equilibrium position. This kind of motion is called overdamping. So in overdamping, when the body is released from the extreme position, that means an oscillation starts from the extreme position. When the body is released from this extreme position, it slowly comes back to the equilibrium position. That kind of motion is called overdamping. Why this slowly comes back to equilibrium position? Damping frequency is very high. That means air resistance is very high. In that case, body slowly comes back to equilibrium position. So we have to derive the general solution of this kind of motion. So in this equation, in general solution, we have one term k square minus omega 0 square. So if k is greater than this omega 0, this quantity is always positive. So we can substitute this as beta. This is for simplicity. Here we put this as beta in equation 1. So the equation 1 changes to, equation 1 becomes x equal to a1 e raised to minus k plus root of k square minus omega 0 square is a positive number. So we put this as beta. This beta is a positive number. Minus k plus beta into t plus a2 e raised to minus k minus beta into t. So what is the aim of this derivation? Still a1 and a2 are unknown constants. So we have to find out the value of these two unknown constants, a1 and a2. So to find out the value of a1 and a2, here put this equation as 2. And we know at extreme condition or at extreme position, this is the extreme position, this is x equal to a. So when at extreme position, from this position, oscillation begins. Okay, so when we release the body from this position, it goes to the next extreme. So the motion starts from this point. So here when t is equal to 0, that is the initial condition, motion going to begin. So t is equal to 0. Here velocity is also equal to 0. Okay. So this condition, this is called the limiting case of oscillation. So we can apply this condition here when x equal to a, that is the body is at extreme position, time t is equal to 0. So we get x equal to, that is a is equal to, x changes to a1 e raised to minus k plus beta into t is equal to 0. So we get this term as e raised to 0 plus a2 e raised to minus k minus beta into t equal to 0, that is equal to 0. So we know that e raised to 0, what's the e raised to 0? E raised to 0 is equal to 1. So we get a is equal to a1 plus a2. So this is equation number 3. Still we didn't get the values of a1 and a2. So to get a1 and a2, then we differentiate this equation 2 and applying this limiting case. So we get a is equal to a1 plus a2. We have to find out the value of a1 and a2 separately. To get the value of a1 and a2, we differentiate this equation 2 with respect to t, then apply the limiting cases. Okay, so while differentiating equation 2 with respect to t, dx, when differentiating that one, we get dx by dt. So this dx by dt is equal to a1 is the coefficient, a1 into e raised to term. While differentiating that term, the result is e raised to minus k plus beta into t itself, into, then differentiate e raised to this term, that is minus k plus beta. Then second term, a2 is the coefficient, e raised to term that itself, e raised to minus k plus beta into t into minus k minus beta. Then apply the condition. When t is equal to 0, dx by dt is equal to 0. That is dx by dt is equal to 0 equal to a1 e raised to minus k plus beta into t. That is t is equal to 0. So e raised to 0. What's the value of e raised to 0? It is equal to 1. So we can write minus k plus beta plus a2 into e raised to 0, it is 1 into minus k minus beta. Then open the bracket. So we get a1 into minus k plus a1 into beta plus a2 into minus k minus a2 into beta. Then from a1k and a2k, take k as the common term. So we get 0 equal to minus k into a1 plus a2 plus, from a1 beta and a2 beta, take beta as the common term. So beta into a1 minus a2. From equation 3, what's the value of a1 plus a2? a1 plus a2 is equal to a. So we can substitute minus ka plus beta into a1 minus a2. Okay. Then from this we can rewrite a1 minus a2 is equal to, take ka into LHS, ka, then divided by beta. This is equation number 4. So from 3 we get a1 plus a2. From 4 we get a1 minus a2. So from these two values we can find out the value of a1 and a2 separately. This is a1, equation number 3 is a1 plus a2 is equal to a. This is equation number 3. So by adding these two equations, 4 plus 3, while adding two equations, add LHS separately, then add RHS. Okay. So while adding these two equations, a1 minus a2 plus a1 plus a2. So this a2 cancel. We get 2a1, that is equal to ka by beta plus a, or we can rewrite this as a1 is equal to, dividing this by 2 and take a as the common term. So a into a by 2 into 1 plus k by beta. So we get the value of a1. a1 is equal to a by 2 into 1 plus k by beta. Then we get the value of a1. If we substitute the value of a1 in equation 3 or equation 4, here 3 is the simple equation. Okay. So here if we put the value of a1 in equation 3, we get a2 as a2 is equal to a by 2 into 1 minus k by beta. So we find out the value of A1 and A2 separately. Then we can substitute the value of this A1 and A2 in this solution. X equal to A1 e raised to minus k plus beta into t plus A2 e raised to minus k minus beta into t. Okay, values of A1 and A2. While substituting the values of A1 and A2 in equation 2, we get the solution of overdamped motion. X equal to A by 2 into 1 plus k by beta into e raised to minus k plus beta into t plus A by 2 into 1 minus k by beta into e raised to minus k plus beta into t. So this is the solution of overdamped motion. From this solution, we have to explain the nature of motion. So in spring mass system, if it is overdamped, what kind of motion is there? If we release the body from the extreme position, that is from x equal to a, it slowly comes back to the equilibrium position and never crosses the equilibrium position. If it crosses the equilibrium position, it becomes oscillation. Okay, but here the body slowly comes back to the equilibrium position and never crosses the equilibrium position. That is the nature of motion. So from this mathematical equation, we have to explain that motion. For this, we can take the standard solution of simple harmonic motion. What is the standard solution of simple harmonic motion? X equal to A sin omega t plus phi. This is the general solution of simple harmonic motion. Two terms are there, A into sin omega t plus phi. A means amplitude, it is a single term, so it is constant. Then sin omega t plus phi, what's the meaning of sine function? If sine function is associated with a mathematical equation, that equation is periodic in nature. Periodic means it repeats in regular intervals of time, or that body is oscillating. This is the meaning of sine function. Okay, first we check whether this equation contains sine function or not. This equation, there is no sine function. So we can state this motion is aperiodic or non-oscillatory. So the first point is in equation 7, no sine function. So the motion is aperiodic. This is the first point. Then second term, amplitude. So this long equation, this represents the term amplitude, A by 2. Which are the terms associated with A by 2? 1 plus k by beta. K means damping frequency. It represents damping. Then what is beta? Beta is root of k square minus omega 0 square. That is when we remove the natural frequency from damping frequency, this beta also represents damping. So k by beta, this is also a damping term. Then e raised to minus k plus beta into t. What's the meaning of e raised to minus k plus beta into t? Means e raised to kt into e raised to beta t. We can write two separate terms. E raised to minus kt plus beta t means e raised to minus kt into e raised to beta t. E raised to beta t. This term represents damping. Then e raised to minus kt. E raised to minus kt means 1 by e raised to kt. That is when time increases, what happens? Exponential when time increases, amplitude A is equal to exponential decrease of this amplitude occurs due to the presence of e raised to minus kt. Okay. So the first term is over, then plus A by 2 into 1 minus k by beta. 1 minus k by beta means this is also a damping term. Then e raised to minus k minus beta into t. That is e raised to minus kt into e raised to minus beta t. Minus beta t is also associated with damping term. E raised to minus kt means this term is common in these two terms. So e raised to minus kt, if we take e raised to minus kt as the common term, what is the result? When t increases, exponential decrease of amplitude occurs. Okay, so from this equation, we can explain the motion as due to the absence of sine function, motion is aperiodic or non-oscillatory. That means it never crosses the equilibrium position. Okay. This is extreme position. When we release the body, it slowly comes back to equilibrium position x equal to 0. and the oscillation dies out. That means the motion stops at equilibrium position. It never crosses the equilibrium position. How can we say that there is no sine function? If sine function is not there, motion is aperiodic or non-oscillatory. Then all the terms represent damping. And one more term is there, e raised to minus kt. So due to the presence of that e raised to minus kt, when time increases, exponential decrease of amplitude occurs. Why this motion slowly comes back to the equilibrium position? All the terms represent damping. Okay, so due to this term, we can state that the body very slowly comes back to the equilibrium position. So the example of this overdamped motion is door closer. So if a door closer is attached with a door, we can pull that door and then we release the door. It slowly comes back to the equilibrium position. Okay, it never crosses the equilibrium position. The motion is very slowly in nature. That kind of motion is called overdamping. So if you represent the graphical representation of this motion, the graph is like this. Time is taken along the x-axis and displacement is taken along the y-axis. X equal to 0 is the extreme equilibrium position and x equal to a is the extreme position. So the motion begins from the extreme position. So when we release the body, it slowly comes back to the equilibrium position. Okay, t is equal to 0. This graph represents overdamped motion. So in overdamping, due to the presence of e raised to minus kt, when time increases, exponential decrease of amplitude occurs. Due to the absence of sine function, motion is aperiodic or non-oscillatory. Okay. The second case is k equal to omega 0. What is k equal to omega 0? Damping frequency becomes equal to the natural frequency. And this condition is called critical damping. Critical damping. So in critical damping, we know the general equation is x equal to a1 e raised to minus k plus root of k square minus omega 0 square into t plus a2 e raised to minus k minus root of k square minus omega 0 square into t. This is the general solution of damped harmonic motion. So when k equal to omega 0, what happens when k equal to omega 0? Damping frequency becomes equal to natural frequency. This term becomes equal to 0. If we put that as 0, what happens to our equation? If x equal to a1 e raised to minus k, the second term is equal to 0. So we get e raised to minus kt plus a2 into e raised to minus k into this term is equal to 0. When k equal to omega 0 minus kt. So we can take e raised to minus kt as the common term. Then we get e raised to minus kt into a1 plus a2. a1 and a2 are two unknown constants. So by adding two constants we get another constant. Okay. So we can write if a1 plus a2 is equal to a, we get e raised to minus kt. Again we get a single valued solution. While solving the differential equation of damped harmonic motion, we take x equal to a e raised to alpha t as the general solution. We get two values for alpha. Okay, so this single valued solution is not a solution of our damped harmonic differential equation of the damped harmonic motion. So we have to modify this case. If we put this equal to 0, this solution is not a solution of that differential equation because we get two values of alpha and we modify the solution as a1 e raised to alpha 1 into t plus a2 e raised to alpha 2 into t. So this is wrong. We have to modify that condition. For this, here we take k equal to omega 0. That means exact matching of two frequencies, damping frequency and natural frequency. It is not possible. There is a minute difference between two frequencies. Here we consider that minute difference. That is, here we take the condition as k is nearly equal to omega 0 and it is not equal to omega 0. It is not exactly equal, but it is nearly equal. But there is a small difference between these two frequencies. Here we consider that small difference. That is, we take, if there is a small difference between k and omega 0, we take the difference, we get that small value as h. Okay, so we can substitute h as a small quantity or a small number in equation 1. So the equation modifies as x equal to a1 e raised to minus k plus h into t plus a2 e raised to minus k minus h into t. So this is e raised to m plus n form. What is e raised to m plus n? E raised to m plus n is e raised to m into e raised to n. So we can write in that form. So a1 into e raised to minus kt into e raised to ht plus a2 into e raised to minus kt into e raised to minus ht. So in these two equations, e raised to minus kt is there. So we can take e raised to minus kt as the common term. So e raised to minus kt into a1 e raised to ht plus a2 e raised to minus ht. So inside the bracket, exponential term is there. Outside the bracket, exponential term is there. Then how can we solve this equation? So in this case, if exponential term is there, we consider the linear series of this exponential term. We studied e raised to x. What is e raised to x? E raised to x is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus etc. If it is e raised to minus x, the linear series is 1 minus x by 1 factorial plus x square by 2 factorial minus etc. This is the linear series. We know h is a small quantity. So the higher powers of h is very small. So we can neglect the higher powers of h. So we can expand the term. Write e raised to minus kt itself into a1 into e raised to ht in this form. So 1 plus x by 1 factorial. Here x is ht. So ht by 1 factorial plus h square t square by 2 factorial plus etc. plus a2 into e raised to minus ht. What is e raised to minus ht? 1 minus ht by 1 factorial plus h square t square by 2 factorial minus etc. Okay. So higher powers can be neglected because h square, it is very small. So we can neglect the higher powers in the two terms. So the remaining term consists of e raised to minus kt into a1 into 1 plus ht plus a2 into 1 minus ht. Then open the bracket. So we get x equal to e raised to minus kt into a1 plus a1 ht. Okay, while opening the bracket, we get a1 plus a1 ht plus a2 minus a2 ht. Then we can write a1 plus a2 as a single term. Then take ht as the common term. So we get e raised to minus kt into a1 plus a2 plus ht into a1 minus a2. So we can substitute a1 plus a2. a1 and a2 are two constants. So we can put a1 plus a2 is equal to a and a1 minus a2 into h. This is equal to b. Therefore, x equal to e raised to minus kt into a plus b. So this is the solution of critically damped motion. X equal to e raised to minus kt into a plus bt. Then we have to explain the motion by comparing this equation with the general solution of simple harmonic motion. Okay. So what's the general solution of simple harmonic motion? It is x equal to a sine omega t plus phi. This is the standard solution of simple harmonic motion. Compare these two equations. Is there any sine function in the solution of critically damped motion? No, there is no sine function. So the first point is motion is aperiodic or non-oscillatory. That is the first point. This motion also there is no oscillation due to the absence of sine function. So while comparing the motion, here no sine function is there. So the motion is aperiodic or non-oscillatory. Then second term is amplitude. This is the expression of amplitude. So here amplitude is we get a plus bt into e raised to minus kt. That term represents amplitude. So a plus bt. What is a plus bt? It is a linear term. What's the meaning of linear term? If t increases, x also increases. That is called a linear term. If we take a and b are two constants, when t increases, x also increases. That means when t increases, initially amplitude increases. That means there is a tendency to move faster because due to the presence of this linear term. But the second term is e raised to minus kt. This term we studied in overdamped case also. Due to the presence of e raised to minus kt, e raised to minus kt is 1 by e raised to kt. Okay, e raised to minus kt means 1 by e raised to kt. What happens if this term is there? When time increases, exponential decrease of amplitude occurs. Okay, so here we get amplitude as e raised to minus kt into a plus bt. A linear term is there. Consider the linear term separately. What happens due to the presence of that linear term? When time increases, displacement increases. When t increases, x increases. That is called a linear term. T is equal to 1, 2, 3, etc. X is found to be increasing. That is linear term. Due to the presence of this linear term, displacement is found to be increasing initially. But e raised to minus kt is associated with that term. What's the importance of e raised to minus kt? If that exponential term is there, e raised to minus kt means 1 by e raised to kt. When time increases, that means higher values of t, this term becomes more relevant. So there is an exponential decrease of amplitude occurs for the higher values of t. For the small values of t, a plus bt is more relevant. So the motion moves, so the body moves in a faster way compared to overdamped motion. But due to the presence of e raised to minus kt, for the higher values of t, there is an exponential decrease of amplitude occurs. So the body comes back to the equilibrium position in a faster way compared to that overdamped motion. Why the motion become faster one? Due to the presence of this a plus bt. In both the cases, there is no oscillation due to the absence of sine function. So the example for this critically damped motion is the point type devices. Point type devices means the speedometer needle. If the vehicle moves in 40 km per hour, the needle moves from 0 to 40 in a faster way, and then it remains stationary at that 40 reading. Okay, that kind of motion, that is called a critical damping. In both the cases, in overdamping and critical damping, there is no oscillation. In critical damping, body moves in a faster way and stays at the equilibrium position. This is critical damping. If we draw the graph of this critically damped motion, so in x-axis we take time and y-axis we can take the displacement. This is x equal to 0, equilibrium position, and this is extreme position. When we release the body from the extreme position, it comes back to the equilibrium position faster than the, it comes back to the equilibrium position faster than overdamped motion. Okay, this is critically damped motion. Critically damped. If we draw the overdamped in the same graph, the motion is very slowly in nature. Okay. So this curve has more bend, so it take more time to come back to the equilibrium position. That's the difference between overdamped and critically damped motion. Both the cases there is no oscillation. Overdamped means it very slowly comes back to the equilibrium position. Critically damped means it comes back to the equilibrium position little bit faster compared to overdamped motion. Okay.